analysis of probabilistic programs. Please go ahead.
Okay, and thanks Andrew for the introduction. And can everybody hear me? Okay, great. So yeah, good afternoon. I'm Wang from Peking University, and today I'm very glad to have this opportunity to present our work on this so-called Newtonian Program Analysis of probabilistic programs. And this is basically based on a collaboration with Professor Thomas Reps from University of Wisconsin-Madison. So let's first review a typical pipeline of data flow analysis using example program shown on the slide here. The program is a very simple imperative program which defines a recursive procedure X. The program is probabilistic in the sense that it makes some random choices to determine its actual control flow. For example, as marked in yellow on the slide, prob 1/3 makes a random choice so that the conditional branch takes the then branch with probability 1/3 and the else branch with probability 2/3. In the else branch, you basically make two consecutive recursive calls to the procedure X itself. The program analysis pipeline usually can turn the program into a suitable IR, for example, a control flow graph. On the control flow graph, we allocate each control flow edge with an action. For example, random choice with probability 2/3, which I just write like P with 2/3 on the control flow graph, and also like the procedure call to X, which I allocate call X as the control flow edge action. Next, the pipeline can use an abstract engine to turn the control flow graph into a data flow equation, usually with a suitable algebra such as semiring. The solution to this equation corresponds to a particular program analysis. For example, the termination probability of the procedure X. And using some proper solver, we can solve the algebraic equation shown on the third card that, okay, the procedure X shown on the first card, it will terminate with probability 1/2. In an interprocedural setting, the data flow flag can also serve as a procedure summary for X, which means that whenever you call X, you can directly use 1/2 as the termination probability. This pipeline we just reviewed corresponds to the well-studied functional approach to interprocedural data flow analysis. Suppose that we want to analyze a program with multiple procedures. And as the pipeline showed in the previous slide, we can establish a system of data flow equations where each unknown variable xi stands for the summary of the procedure pi. We can then solve the equation system by generic iterative algorithm to find successive approximations, such as the cleaning iteration. As demonstrated here by the animation, we start from some bottom element in an abstract domain, and we approximate the solution iteration by iteration. So in terms of the termination probability analysis, we can first interpret the equation using the abstract semantics for termination probabilities. Basically, it's a domain of real numbers from 0 to 1. For example, we can interpret the program action skip as probability 1 because the program skip always terminates and the atom prob 1/3 with probability as the probability 1/3. Then the algebraic operations, the extend or the circle times, we just reinterpret it as multiplication because the extend means the consecutive composition of two programs. So termination probability of two programs we can just calculate it by a product of the termination probability of two programs. Then for combine, which I just use the circle plus, which means we just interpret it as the addition of probabilities because for combine, it means we want to combine the two different control flow paths on the control flow graph. So we can just sum up the termination probabilities. So after we replacing all the algebraic operations with the Euro numeric operations, we obtain a standard numeric and also quadratic equation. And if we use cleaning iteration, we reviewed in the previous slide, we obtain an infinite sequence of successive approximation from 0 to 1/2. Note that it can take like an infinite number of iterations to reach the final answer. But for this kind of numeric equation, there's another generic solver based on Newton's method. So does everybody like in this room already be familiar with Newton's method? Okay, so I think I can stop at this step, but just to recap some of them, some of the essentials. It's also like an iterative algorithm which makes successive iteration to compute the root of a function. So the idea is that for given a function f, we can construct like a linear model of the current approximation. So for example, we start with xi, we compute the derivative of fxi, then we construct a tangent line through the point xi, fxi. And then use the crossing of the x-axis and this tangent line to be the next approximation, xi plus 1. And we just repeat the process. Okay, then we are approaching the actual root just like by repeating the whole process. But you can still notice that like we still need an infinite number of iterations in theory. But how does that go back to the termination probability analysis? The simple way is that we can move the left-hand side to right-hand side. Then we can obtain a function f. Then we just reduce the termination probability analysis to finding the root of this function f. So if we just repeat this process, so we can construct like another sequence, which I just knew here, another infinite sequence of numbers, and finally we will reach the true answer, 1/2 as the termination probability. But both cleaning iteration and Newton iteration, as I said, they all cause like an infinite number of iterations to converge, but which will converge faster in practice. So just plot like the two sequences we just seen for the termination probability analysis, and the blue one stands for the cleaning iteration, and the Newton one and the orange one stands for the Newton iteration. And as you can see, because the ground truth is 1/2, and Newton iteration can converge faster than cleaning in this setting. So can we apply the Newton method as a generic equation solver to program analysis? The answer is yes. In 2008, Esparza et al. Proposed Newtonian Program Analysis, which applies Newton's method to interprocedural data flow analysis. The overall idea is that this is the basic scheme for cleaning iteration. But for Newton iteration, we want to construct a linear correction term per every iteration. And the high-level idea, we can also demonstrate this kind of Newton iteration visually by so one Newton iteration will basically make multiple cleaning iteration, and then it will converge to the final solution with fewer steps. Then, so how does this linear correction term be constructed? So the idea is that we can just define some syntactic linearization, which is very similar to the derivative from the calculus. Because now, if we think of a semiring contains both like a multiplication and an addition operator. So we can just define this syntactic linearization rule similarly. For example, the sum. The derivative of a sum is basically the sum of derivatives, and then the derivative of a product is basically, we just follow the standard Leibniz rule to define the syntactic linearization. No, all of those don't need to have any concrete meaning because they are just syntactic. Then in the Newton iteration for program analysis, we just construct a linear equation in every iteration. And here I just change the unknown variable from x to y. And as you can see, like for each at the highlighted part in the yellow, this is the linear correction term, which and this is how it's actually defined. So the basic idea is that we compute the derivative of the function at the previous solution to the equation, and then we just use that to construct a linear function by multiply it by y to construct a linear model of the original equation. But I have to note here is that this formula is inexact, and just use that for brevity because in general, semiring does not have to be commutative. But if we assume like the extent is commutative, then we can obtain this form here. And to see why this is a linear correction term, For example, if the original function is x times x, and I want to find its linearization at nu, it will become x times nu plus nu times x. As you can see, if like the multiplication is commutative, you would basically get to like 2 times nu times x, something like that, as what we can see from the calculus. And also for another example, if we want to compute the derivative of b times x times c, where b and c are two constants, at the old value nu, it will become b times x times nu times c plus b times nu times x times c. So those terms are all linear because every consummation in the expression, they at most involve one variable. So if we go back to the termination probability analysis, what does that mean? Which means that, okay, we start from the original equation, we do the linearization, then we obtain a linearized equation. So if we can demonstrate that visually, so here's a control flow graph for the original equation for the recursive procedure x. We can also do this visualization for the linearized equation. As you can see that we have one more pass from the function entry to function exit, but then from every entry to exit path, there is at most one procedure call where I mark in yellow. Here is something. It seems like the Newtonian program analysis in trying to do some exploration. For example, for the left path, it performs exploration for the first call, and for the second call, it reuse the previous solution nu as a procedure summary. And for the second pass, it will reuse nu for the first call, but then perform exploration on the second call. And finally, it will combine the results using the combine operation. Okay, so if we plug in the whole stuff back into the program analysis pipeline, so this one month we can, again, interpret all the algebraic operations by their interpretation, basically numerical interpretation, obtain a linear equation, which can be solved very easily, and they can obtain the iteration scheme for Newton's method to solve termination probability analysis. So far, we just talked about something that can already be done by the framework developed by Esparza already in 2008. So the whole framework is Newtonian. It can handle probabilistic programs. It looks very promising. Indeed, Newtonian program analysis is suitable in this case because due to the quantitative nature of probabilistic programs. But there's one key missing part for the whole story is that we only consider one combined operation, but in practice, probabilistic programs can have multiple kinds of branching, like probabilistic ones, non-deterministic ones, and conditional ones. So the actual work we did in our paper is to tackle this key challenge. So how to extend Newtonian program analysis to support multiple combined operation. So I'm not going to go into the technical details of the whole pipeline of our work, but I will just revisit the whole pipeline to see where we need to do some change to support this kind of multiple branching stuff. So the first thing is that we need to change the intermediate representation, which is the control flow graph here, because here on the control flow graph, like for the branching or confluence nodes, they are interpreted by the combine operation. But now if we want to support multiple combined operation, we need to first kind of distinguish the different kinds of branching in the graph already. So our solution is to use control flow hypergraph, where the hypergraph means like a normal direct graph where each hyperedge can have one source node but multiple destination nodes. To see why we need that, consider this kind of non-deterministic program, which will first make a non-deterministic choice, and then in one branch, it assign x with value 1 or 2 with probability 1/2. And in the other branch, it also assigns randomly to variable x with value of 3 or 4 with probability 1/2. So we can represent the control flow of this program as a control flow hypergraph in the sense that we have these yellow edges, which are just hyper edges. It has one source node and 2 destination nodes to represent such kind of control flow. The good thing is that when we're composing hyper edges together, we get hyper paths, which is basically some tree structure as a generalization of program execution paths. The good thing is that we can distinguish like execution paths from different distributions. For example, here we have two non-deterministic choices, so we can finally in semantics we have two different distributions. So once we have this control flow hypergraphs, we can then think about, okay, how can we represent this kind of control flow hypergraphs as a data flow equation algebraically? So the idea is that we can represent this control flow hypergraph as a tree expression. The high-level idea is we can unfold the control flow graph from the entry node to the exit node. Then we can obtain like a tree-like structure where every root leaf path stands for execution path in the original control flow hypergraph. Then we can also turn it into a finite expression, like a tree expression. We can raise the expression outside in. The first is a non-deterministic choice, followed by two branches. One branch will have, both branches have a probabilistic choice, which assign to program a variable x with different values. Then we can use as a generalization of semirings, which we call Markov algebras, which is basically semirings plus multiple combined operations as the as a semantic model for our program analysis. So basically, to have like a semiring structure for the abstract semantics, then we have different combined operations. This circle plus with a subscript, it stands for probabilistic and conditional branching. And the squares cap, it stands for non-deterministic branching. So after we turn the whole control flow hypergraph into an algebraic equation, then the next step is to solve the equation by Newton's method. So we just follow the idea of Newtonian Program Analysis. What we need to do is just to define some syntactic linearization rule for the new operations we introduced in Markov algebra and prove they are sound. And in this case, we can do very similar to this equation we have seen earlier in the presentation. And also visually, I would like to stress it's similar to the visualization of control flow graphs. Now we have these tree-like structures. Originally, we have this tree on the left. On the right path, we have two consecutive procedural calls. And after the linearization, we obtain a more complex tree. But then on every root to leaf path, there's at the most one procedural call, which makes all of the program linear. So finally, then after we obtain the linearized equation, we need to solve them. But unfortunately, currently we don't have a generic way to do that so it requires each program analysis to provide a strategy for solving these linearized equations. We did some case studies on 4 different program analyses. Here just show the evaluation results for 2 of such case studies, one for termination probability analysis, and the other for moment of reward analysis. We compare our efficiency against clean iteration on some synthesized benchmark programs, and the point in the lower right triangular region means the benchmark of our method can be faster than clean iteration. So to summarize, the key takeaway is that in this work, we extend Newtonian program analysis to support multiple combined operations, so as to enable analysis of programs with probabilistic, non-deterministic, and conditional branching. And you can find more in the paper about how can we support loops and unstructured control flows, how do we prove the soundness, and also more case studies. Especially there's one very interesting one about invariant analysis. And thank you, and thanks for your attention, and questions are welcome.
So we have time for one quick question. Maybe you want to set up while we take the questions.
Hi, very nice talk. So I was wondering, does this method also extend to programs with continuous probability distributions? Or is it only discrete branching that is?
Yeah, that's a good question. So it actually works with continuous probability distributions. So actually, if you can have an instantiation of the Markov algebra that can work with continuous distributions, then it seems to be fine. And in one of our case studies, we actually support continuous distributions.
All right. Thanks. Very nice work.
Right. Thank you again.